Hello students, today we will start chapter 6 Work, Energy and Power. First of all, we will see the definition that work is said to be done by a force acting on a body provided the body is displaced actually in any direction of the force except in a perpendicular direction of the force. In class 9th also you have learned this, the definition of work, in which we'll see the first condition, the work is said to be done when the displacement is there. Okay, that means suppose a boy is pushing the wall, and when the boy is continuously pushing the wall is not moving at all, but the boy get tired. In such situation, we see that there is no displacement in the wall. That means the wall is not displaced. So we cannot say here that the work has done because the displacement is 0. Okay, that means when the work is said to be done when the displacement is there. Second thing, as we have learned in class 9th, that time we have not knowing about the vectors and the components, so we are just studying about the we have studied about the simple case. That means a force is applied in this direction and the displacement is also in the same direction, and in such situation we are telling the work done is equal to, that is equal to force into displacement. Okay, but what happened, you will see here, suppose a force is applied in this direction on the object. Suppose this is the object, it is a point size object, and in this point size object the force is applied in this direction. Okay, but the displacement take place in this direction. As you have seen in case of the carom board, that means when the striker is strike to a coin, the coin is displaced, but always you will find whatever the direction the force is applied, the displacement will take place in some other direction. So here the same case you will see, the force is applied in this direction and the displacement will take place suppose in this direction, just by making angle theta in the direction of the applying force. So what we can say, the component which is working in the direction of the displacement, the component of the force which is working in the direction of the displacement is equal to F cos theta. That means if we are calculating here the work done, in that situation we can say force multiplied by displacement, but this time the force which is working in the direction of displacement is F cos theta and the displacement is S. So this is F cos theta, or simply you can say Fs cos theta. So work done is equal to Fs cos theta. But according to the definition of the dot product, as we are knowing, the dot product is the scalar product of two vectors quantity. So here you will find the force is a vector quantity, the displacement is a vector quantity, and the magnitude of these two is multiplied by the cos theta, where the theta is the smaller angle between them. So in that situation we can write this as F dot S, the work done as F dot S. Okay, so actually the work done is the scalar product of force and displacement. That means the work is a scalar quantity and it can be given, the magnitude of the work is given by Fs cos theta, that is the magnitude of force, magnitude of displacement, and the angle between them means cos of the angle between them. Okay, so this way the work done is given. Okay, now you will see here, in case of, suppose the force is working in this direction and the displacement take place perpendicular to the applying force or perpendicular to the direction of applying force. So what you will find here, the work done is equal to Fs cos theta, but theta is 90 degrees, so it is cos 90 degree. So whatever the force is there, the value of the magnitude of the force, or simply the magnitude of the displacement, whatever it will be, but because it is cos 90 degree and value of cos 90 degree is 0, so 0 is multiplied by any of the quantity, the product will be 0. That means the work done is 0. Or simply what you can say, no work has done. You can say no work has done, or the 0 work is there. Okay, so now you will understand, you may understand here why we are calling here the work is said to be done. Why we have given the definition, the work is said to be done when the displacement will take place by applying a force on any of the object, but the displacement must not be in the perpendicular direction from the direction of the applying force, because in such situation the work calculated is 0. Work done by constant force. Constant force, that means a constant magnitude of force is applying on any of the object. So when a constant force, suppose F, acting on a body, so produces a displacement S, suppose displacement S in the body, then work done, we'll see the work done by the force is given by the dot product. Just now as we have seen, the dot product of force and displacement. So we have seen here the work done is equal to F dot S, where we'll find F, and this is S vector F and vector S, that means force and displacement. The angle between them is theta. This is the smaller angle between them, the force and the displacement. So the work done is given here as Fs cos theta, and as I said to you, this theta should be small angle, that means less than 180 degree. So theta should be this small angle between force and displacement. Okay, now we will see types of work. First of all, we'll see zero work. Zero work, as we know, here the work done is equal to F dot S, or we can say Fs cos theta, where F is the force, S is the displacement, and theta is the angle between them, the small angle between them. Okay, so if the resultant of Fs cos theta is 0, that means the work is said to be 0. And how it is possible? For example, because the work done is equal to Fs cos theta, so here three conditions are there that the product of this quantity will become 0. When the force is not applied, that means simply we can say if force is not applied, that means F is 0. So the work is 0. That work is 0. Or we can say the force is applied but the displacement will not take place. That means S equal to 0. Then also the work would be 0. Or the force is applied and even the displacement will take place, but it will be in the direction perpendicular to the direction of the applying force. So in such situation, the angle theta is 90 degree and cos 90 degree will be 0, and so on. You will see that the work done would be 0. That means these are the three conditions in which the work done is 0. And in this three condition, the work is said to be 0 work. For example, we'll see here some example. So if we see, when you will see here, if we apply a force on the wall, simply if we apply a force on the wall, okay, we know that we will just fail to move the wall an inch. So in that situation the displacement is 0. In that situation the displacement is 0, and so the work done is also 0. Okay. Another case that you can see here, when a laborer carrying a load on his head, and in that situation also the work done would be 0 because theta angle is 90 degree. That means the displacement and the applying force will make 90 degree angle with each other, and so that it can say here, we can say here the no work is done. Okay. Even no work is done when the satellite revolve, because you will see here the case when satellite revolve around a planet. So this is, you can say here, this is a planet, and in this orbit a satellite is revolving around the planet here. Okay. And as we know, in the uniform circular motion, or you can say simply, suppose a object is moving in a circular motion, the direction of the velocity is given always tangential to the point where the object is. Suppose the satellite is here, so in that situation the velocity will work in this direction. This satellite is moving, you will say that anti-clockwise direction, so the velocity will be given in this direction at this point. Okay. Now suppose the satellite will reach this point in the orbit, so it will be, the direction of the velocity is also given here as tangent to this point, that is v. So magnitude wise this v will be equal, but the direction is continuously changing, and this direction is changing due to the inertia of the direction, because every object is having the tendency to keep its direction constant, and it is moving tangential direction, but because of the gravitational force between the planet and the satellite, the planet has given the centripetal force. That means the gravitational force will provide here the centripetal force to the satellite, and so that the satellite will revolve around an fixed orbit. Okay. But here you can see that if whatever the direction the velocity will be, that means it is moving in the tangential direction. That means the displacement will take place in the tangential direction, but the centripetal force is working toward the center of the planet. So the centripetal force is working here in along the radius of the circular path or the circular orbit. So what you can say, this tangent and radius will make angle between them 90 degree, and because of that the angle theta is 90 here. And as we know, just now we have seen the case when the theta angle is 90, or the angle between the force and the displacement is 90 degree. In such situation the work done will be zero, and this is called zero work. So no work is done when the satellite revolve, and because of the angle between the force and the displacement is 90 degree. Positive work, when the angle between when the angle between force and displacement is less than 90 degree. That means, suppose this is the direction of the force, so the displacement must be less than this. That means from 0 angle to less than 90. Till here you can say when the displacement is, so the work done is called positive, because in that situation you will find here that cos theta, the value of the cos theta must be in first quadrant and it is positive. The value of theta, cos theta, that is in the first quadrant, and in the first quadrant cos theta is equal to positive. So when theta is less than 90 degree, then cos theta will be positive, and so that the work done, which is Fs cos theta, will be also positive. Okay, and this is called positive work. For example, we'll see here, when we stretch the spring, this is the spring, and when we stretch it, so while stretching we are applying the force from both direction. This way the force here or the force here we can apply, and you will see that the displacement also will be here or here. Okay, so what you will observe here, in this case the angle theta is 0, and so the value of cos theta will be positive, and you will find the work done is also positive. So while stretching the spring, the work done is positive. Even compressing the spring also, the work done is positive. Okay, next the example we can see here, that is the second example. When a body falls freely, when a body falls freely, you will see that like this way. This is, suppose an object is here, and when it is falling freely, so because the force which is working here is the gravitational force, and the direction of gravitational force will be toward the center of the earth, that means downward in this direction, and you will find the displacement also is in this direction. The angle between this displacement and the force is 0, and so that the work done is positive. So these are the example of the positive work. Negative work, when the angle between force and displacement, force and displacement is more than 90 degree but less than 180 degree, or you can say less than or equal to 180 degree, then the value of theta will be in the second quadrant and cos theta in second quadrant will be negative. So what we can say here, the value of cos theta in second quadrant will be negative, and so that the work done is also negative. The work done is also negative because we know that in the second quadrant, like from 90 degree to 180 degree, this way if theta angle will be, that means the force and this is displacement, you will see, that is they are making the angle. Suppose force is in this direction, okay, and the displacement is in this quadrant, so the work should be negative, the work would be negative, okay. For example, you can see here, this is a case. For example, we'll see when a force is applied in this direction, this is the direction, and the friction force is working here in this direction, just opposite to the force applied. The displacement is also in this direction. So if we calculate the work done by the force of friction, because you will see the displacement and the friction, these are working at 180 degree angle, so the work done by the friction force will be negative. Next case we can see here, second case, that when we pull a bucket of water from the well, then this is, suppose a well is here like this way, okay, and from this well a bucket of water will be drawn like this way with the help of pulley. With the help of pulley, a pulley is there, this is a pulley, okay. So the person will apply the force in this direction. The person is applying the force downward just by pulling this rope, and the displacement of this bucket, which is full of water, is in upward direction. So what you will find, the force and the displacement is making angle 180 degree with each other, and cos 180 is -1, so the work done is also negative, okay. So these are the some example in which the displacement and the force are making angle more than 90 degree but less than or equal to 180 degree, and so that the work done is called negative work. Dimension formula of work is m l 2 t to the power -2. Absolute unit of work. SI unit of work is joule, that is equal to Newton meter, or equal to kilogram meter square per second square. CGS unit of work is erg, that is equal to dyne, centimeter equal to gram centimeter square per second square. We know that 1 joule is equal to 10 to the power 7 erg. Now we'll see here gravitational unit of work. The gravitational unit of work, that is the SI unit. As we know, the work is equal to force into displacement, only in magnitude if we are taking here. So it is, you will see the gravitational unit of force is 1 kgf multiplied with this displacement is in meter. So 1 kgf is equal to 9.8 Newton meter, or we can say 9.8 kilogram meter square per second square, that is 1 kg Fm. This is the SI unit of work. Next we will see CGS unit here in gravitational unit of work, that is 1 cm GFcm, that is equal to 1 GF into cm is equal to 980 dyne cm centimeter, that is equal to 980 gram centimeter square per second square. So these are the unit of the work. Now we'll see the vector form of the work, that is vector form of work. If we'll see here that W, that means the work done, is equal to force into displacement, that means force and dot product of displacement, that is equal to Fs cos theta. If we are representing F in 3 dimension, that is Fxi, Fyj plus Fzk, and displacement also xi, yj plus zk. So F dot S is given as x fx y fy plus z fz. That is, we can say here Fs cos theta is equal to x fx y fy z fz. We'll take the sum of this, and if we'll just take the f, the magnitude f, this is equal to fx square plus fy square plus fz square square root, and the displacement is x square plus y square plus z square under root cos theta, that is x fx y fy plus z fz. So if we have to calculate the angle between force and the displacement, and if all these quantities are given here, we can simply calculate it by applying the formula that cos theta is equal to x fx plus y fy plus z fz upon under root fx square plus fy square plus fz square under root x square plus y square plus z square. So this way we can calculate angle theta.